Thanks for being here. Thanks for joining this Back to Basics session. In this session, we'll be covering secure sockets layer or transport layer security. And I'm going to do that in such a way that you don't need a PhD in mathematics, but that mere mortals like you and me can understand. My name is Maarten Mulders. I work for a Dutch consultancy firm, InfoSupport, and we prefer to think of our work as awesome sauce. It's the secret sauce that makes every project better. And you may be wondering, transport layer security, is that awesome sauce or is that a source of headaches? Probably. We've all seen stack traces like these when we were developing our Java software. And it takes some time to find out where the real issue is because the stack trace is rather long and the lines are long. Eventually we may find a message, a bit cryptic though, saying unable to find valid certification path to requested target. That's just an example. There are many more of them. And I don't know about you, but years ago when I would see this, I would typically call this colleague of mine called John and say, John, please help me out. You know this stuff. You know how that works and I don't. Please help me out. Help me in figuring out what went wrong. And I figured that's a bit strange. Why am I doing that? Because nowadays we're building systems that are more and more distributed. And especially now that microservices have become kind of a default. I'm not saying it's a good default, but many people tend to directly start building microservices. And we build systems that are more and more distributed by nature. Secure communications become essential to do that in a good way, because the communication between all those application components and also between our application components and our infrastructure like databases must of course be secure and must be trustworthy. And if that is a prerequisite for success, then how can it be that we're using an important piece of technology that we don't really thoroughly understand? That's kind of a risk, I would say. And that's why I started diving in, figuring out what exactly are we talking about. And the outcome of that is what I want to share with you today. So you may have seen the OSI model for network transports. And if you look carefully at this model, it says in the second layer from the top, it's the presentation layer. It says, well, this layer is responsible for doing data representation and encryption. And that's all nice and good. But it means that whenever we need a secure encrypted transport between two application components or between our application component and our infrastructure components, we are supposed to build this in an application ourselves. Now, what is transport layer security? Transport layer security essentially moves that responsibility of doing encryption of whatever we send and receive down to the transport layer, just in the middle down there. And what benefit does that give us? It means that if we can rely on an end-to-end connection that is reliable, we can also rely on its security. And that's a very valuable thing. So a session like this would not be complete if we wouldn't start out with the history of secure sockets layer and transport layer security. It all started with the description of the SSL 1.0 protocol. This protocol was never released. The engineers that were describing it found it had too many flaws to be of any value. The first published version was SSL 2.0, which was published in 1995, and it stayed of use until 2011. In that year, security researchers published the Poodle attack, and the Poodle attack essentially made SSL 2.0 not trustworthy. In the meantime, an upgrade became available by the name of SSL 3.0. That one stayed of use until 2014. In 2014, it was proven that the Poodle attack could also influenced SSL 3.0, making it essentially untrusty. But developments hadn't stood still. In 1999, TLS 1.0 was published. TLS 1.0 was basically a re-description of SSL 3.0 with a few minor tweaks and improvements. But the engineers who published it thought it was big enough to justify a new name and a new version number. So TLS 1.0 stayed in use until 2011. By then, security researchers published the Beast attack, and the Beast attack was targeted at TLS 1.0, making it untrusty. In 2006, TLS 1.1 was published. In 2008, TLS 1.2 was published, and only 10 years later, just 2 years before today, TLS 1.3 was published. Those latter three are until now not proven to be broken. And I'm not saying they're secure. I'm saying there's no public evidence that you can break it. But the problem is with security, maybe somebody has broken it but did not publish it. That would give them a big advantage because nobody knows that they can actually break that part of encryption. For practical considerations, I would always recommend to use at least TLS 1.2. Over the last years, we've seen major websites migrate to TLS 1.2 or even TLS 1.3. If you're using Java, then you might be aware that, for example, Maven Central has migrated like a year ago, which turned out to be a problem for some users that were still running Java 7. If you are running Java 7, you need to explicitly enable those newer protocols. So, before we dive in, I would like to do a quick demonstration of what the actual problem is that TLS solves for us. In this window, I have a packet sniffer running. I'll start it. The package sniffer is T-Shark, which is part of the Wireshark package. And it lets us listen to any network traffic that comes over the LO0 network interface. You can see this as if somebody would have cut down the UTP cable between your machine and another machine and just is able to inspect each and every packet that flows over that wire and then send it along. Now I'm going to a demo website I have here, which runs on localhost. And if I open that page, it just says lorem ipsum and the rest, which is nothing particularly interesting. But as we can see, since we are able to inspect all network traffic, we can clearly see the HTTP request coming in. And we can also see the HTTP response going back with lorem ipsum and the rest over there. Now, this lorem ipsum generator is, of course, not very interesting, but imagine that this was my secure banking website. Well, it wouldn't be so secure because everyone who was able to intercept the traffic would be able to see my username and password. And you may say, well, nobody is able to cut the cable. Probably not, but how about open Wi-Fi networks? Just as an example. So if we want to address this, we need three things. We need public-private key encryption, we need signed certificates, and we need certificate authorities. And in the remainder of this talk, we are going to dive into that. So the first thing that we need is public and private key encryption. We need public-private key encryption because we need a way to encrypt our traffic, but we cannot exchange keys with each and every individual on the planet. In that case, we would have so-called symmetric key encryption, where the sending and receiving part share the same key. But on the scale of the internet, this is not achievable. So we need public-private key encryption, where there is a mathematical relationship between the public and the private key. And the private key remains the sole property of the one who owns it, whereas the public key can freely be shared with anybody else. Now, as I said, I promised you to explain it in such a way that we don't need a PhD in mathematics. That is what you would typically need if you would really want to understand how, for example, RSA works. But we don't have the time to do that. So instead, I figured we need diagrams that we have used in the past. Diagrams that explain us how we can build furniture from certain furniture shops can also help us in understanding how public key encryption works. So in our example, we are looking at it as if it was a safe, and the safe has a special kind of lock. The lock is special in the sense that there are two keys that fit into the lock. One key allows the lock to switch in one direction, the other key in the other direction. And as you can see here, the key with the lock on it allows us to close the safe, and the key with my face and a head on it is the only key that is capable of opening the safe. And since the public key is public, I can distribute it to the whole world, to each and every one who is interested. Now, if I do that, anybody in the world who wants to send me a message can write their message and put the message in the safe. They will use the public key to close the safe, and then the safe can be put on any transport mechanism that we want to. In this example, it's a truck. The truck is not secure by itself because anybody could rob the truck, but the safe that is on the truck, they cannot open it because they don't have the corresponding private key. The transport mechanism really doesn't matter. It could even be a bunch of pigeons, assuming that they are strong enough to lift the safe, as long as it is reliable enough to bring the safe to me. Now, since I am the only person in the world who has the private key, I am also the only person in the world who is capable of opening the safe and finding the message that is inside the safe. And if it is a lovely message, I will be a happy person because I just received a lovely message. So far, so good. Now, as we may all understand, this is not how it works in reality. There is no safe, there is no truck, there is no letter inside the safe. So let's dive a little bit deeper and look at it from a mathematical perspective. What I'm sharing here is how RSA works, but it's a very simplified approach. The simplified approach is this. In the protocol, we start by selecting two prime numbers, and it doesn't really matter which prime numbers as long as they are prime. We call them P and we call them Q. The next thing is that we calculate the product. So we multiply P with Q and find 187. Third step, we select a random number that lies between 0 and the product. And the random number can be any number. We say this time it's the number 3. And now there's a little mathematical puzzle to solve for you. Can you please find me any number D for which the following equation holds: D multiplied by E minus 1 modulo P minus 1 multiplied with Q minus 1 must be 0. Now, I'm not going to solve it in real time for you. Let me just say that if we solve this, and that's a relatively simple thing to solve because there's just one unknown, the value D, we can solve for D is 107. So far, so good. But note that if I would have selected another value for E, let's say 75, then D would inevitably change, and in this case it would be 183. So as soon as we change this random number, the outcome of this mathematical equation with one unknown also changes. And that's a good thing because it makes it harder to perform so-called replay attacks. By selecting a random number every single time we use this, it's harder for an attacker to intercept encrypted packages and see if they can find a pattern and thus derive the key. Now, we are going to make it a little bit harder. What if P and Q are not known? So imagine I select P times Q, which is 299. I select a random number 5, but I'm not telling you what P and Q are. I'm just saying that the product is 299. And I'm again asking you to solve this mathematical equation to find me the value d. Now, we have a mathematical equation, but it doesn't have one unknown, it has three unknowns. D is unknown, P is unknown, Q is unknown. And although we know the relationship between P and Q, we still have more than one unknown. This turns out to be pretty hard if we don't know P and Q. I have to say, if we do know P and Q, for example, I tell you P is 13 and Q is 23, it is rather trivial to calculate D and find that it has the value 317. And I'm saying it's pretty hard, but it's actually very, very hard. If P and Q are big enough, it will take close to an eternity to find the original values of P and Q if you only know their product. So what does this tell us? I could share P multiplied with Q. I could share the random number E if I wish, and still be relatively safe because I am the only one who knows the individual values of P and Q. That is the private key that only I know, and the public key is the product of P and Q. Now, if we apply this, for example, to text encryption, we could say that our letter started with the letter G for good morning, or something like that. The letter G is the 7th letter of the alphabet. We always operate on numbers when we're talking about encryption, so we need to find a way to convert text to numbers. Again, P multiplied with Q is 187. I'm not telling you what P and Q are. E is 3, and the letter G gives us the number 7. We take the input, we raise it to the power of E, so that's to the power of 3 in this time, to find 343. Then we modulo with 187 to find 156. Now, on the receiving side, I see the number 156, and I happen to know P and Q individually. So I can derive the value for D, which is 107, as we saw earlier. Now I make a little bit complexer calculation. I take this 156 and raise it to the power of D, which is to the power of 107. The outcome of this is roughly 4.6 with 234 zeros behind it. That's a very large number. Your smartphone will not allow you to do this, at least not in the calculator app. Your computer will probably refuse to do this in Excel, but the CPU in itself is more than powerful enough to do this in a very short amount of time. Next, we take this value and we modulo it with 187 again. And guess what? The outcome of that is exactly 7. And 7 happens to be the letter G if we map that back to the alphabet. So since I know P and Q, I am able to get back from this 156, this ciphertext, to the original clear text, which was the letter G. This is a fairy tale figure. I don't know what the fairy tale figure does here. It shouldn't be there. So anyway, what happens in reality when two systems connect? So for instance, your browser and a website, or your application component and another application component, it all starts with a client that wants to initiate the connection. So it sends a client hello package to the server. The server is very polite and will respond with server hello. It will then publish its certificate and exchange some key material. It will finalize this phase by saying, I'm done in the hello stage. Then the client will respond by exchanging some more key materials. And then number 7 is important. It will say, everything that I will send you from now on is going to be encoded using a different cipher. And it will, of course, also tell what the cipher is. And then it will say, I'm finished for now, thank you. The server will reply and say, okay, gotcha. We're changing our encryption methods to use the following cipher spec, and we're done for now. This again is more or less of a simplified version. In reality, the client and the server will use the asymmetric encryption to establish a shared secret for the session so that they can switch from asymmetric to symmetric encryption. And the only reason for that is that symmetric encryption consumes less CPU cycles. So, time for a second demo. Let me clear this screen. Again, I'm going to intercept all traffic, but this time, like so, I'm switching my website to HTTPS. Well, as you can see, the outcome of the website is still the same. Now let's look at the network traffic that happened. Scrolling up and up and up and up. Wait, this is the previous one. There it starts. This is a whole lot of network traffic. The first word I can recognize more or less is localhost. There it says HTTP, which is just a protocol description. And there it says something like mkcert, and it lists my name, which is correct because my name is in the certificate. And then there's a whole lot of unreadable gibberish and more gibberish, and the certificate is there again. And wow, there's nothing here from the lorem ipsum that we used to see the previous time. So if someone was able to intercept our network traffic, he or she is no longer able to do that. We are now in a secured environment where we have a trustworthy connection layer between us and the receiving party. That's a good thing, and I really like this, but we're not there yet. Because we also need certificates. I already said that the server will publish their certificate. What is a certificate actually? Well, a certificate, this is an example of a certificate. It's my driver's license. My driver's license is a document that contains quite a lot of information. It has a subject, which is me. It has a validity, which is the end date. It has a usage, which is what the driver's license is meant for. And a certificate in a computer
Maarten?
is, yes? What's that?
I'm not able to hear you. Not sure.
Oh, well, is it better or?
Yeah, it's okay.
Okay, it's okay, thanks. I hope it wasn't for too long. As I was saying, the driver's license tells something about me, the subject, to anybody who is interested to know that. For instance, police officers who want to verify if I'm allowed to drive a car. And in the computer world, a certificate is more or less the same thing. It tells something about the subject to anyone who is interested. A computer certificate will basically say to anybody, hey, there's a computer down there and it has property of a public key. It also has the private key, but of course, we're not telling you what the private key is. We're only telling you what the public key is. It's valid until a certain date, and it can be used for particular purposes. There's also a fingerprint on the certificate, which is a digital means of verifying that the certificate is authentic. Just as on my driver's license, there's all kinds of authenticity mechanisms to prove it's valid. But anyone could make a certificate, so we also need some other thing that can issue a certificate so that they can prove that it's valid. And therefore we have a signature algorithm, the actual signature and the name of the issuer. So we need some kind of digital signatures. And therefore we can use the same mechanism with public and private keys. This time the safe works different. The private key is there to close the safe and the public key is there to open the safe. So it's a different type of safe. Again, I can write a message, put it in the safe, close the safe with my private key and ship that to anybody in the world. Anybody in the world is able to use my public key to open the safe. And by opening the safe, they can be sure that I was the one who closed it. Now imagine this bad guy over there who wants to make people think that he is me. Well, we don't even look the same. So he has his own private key, closes the safe and pretends to ship a message to somebody else saying that he acts as if he was me. But that person uses my public key to open the safe and the safe doesn't open. So by the fact that the safe doesn't open, that person knows, hey, this safe was not sent by Maarten, although it looks like it was. In the reality of computer systems, by the way, you can open the safe, but you will find that the message does not match. Because mathematically, a signature is a combination of two functions, two mathematical functions. There's a signing function, which takes the message and the private key to generate some kind of a control number, which is the value T. And there's a verifying function, which you can give the message, the payload itself, the control number, the outcome of the previous one, and the public key. And it will either say that's okay or that is not okay. And depending on the outcome, of course, you can decide whether or not to trust the message. So given X and T, knowing the public key, we can tell if the message was indeed signed by the owner of the public key. So far, so good. We're almost there, but we need one more thing, which are certificate authorities. So what is a certificate authority? A certificate authority is basically any organization that issues those digital certificates. And these certificates are used to certify the ownership of a public key to anybody being the subject of the certificate. Well, so far so good. They are able to certify that I have a public key and also have the corresponding private key. What happens here in reality is that if we want to connect to someone that we don't know, the question mark, well, we can't know if they are trustworthy or not. But what we can know is that we have a few friends and trusted people around us. So I happen to know my colleague John, as I said in the introduction. John happens to know and trust Alice, and Alice happens to know and trust the person with the question mark that I'm trying to reach out to. But the question is, who is John in this story? It's not my colleague, for sure. If you look in your computer, in the certificate store of macOS or Windows, in the trust store of a default Java installation, you will find roughly 160 Johns. You will find 160, more or less, certificate authorities. And that basically says that every certificate that they issue is automatically trusted by you. I don't know for you, but I didn't verify their trustworthiness at all, to be honest. So it boils down to me trusting Apple when it comes to my Mac. It comes down to trusting Microsoft when it comes down to my Windows laptop. And it comes down to me trusting Oracle when it comes to my Java environment. In fact, I'm trusting just one party, and I leave it up to you to decide if that's a good decision or not. But that's reality nowadays. Now, the good part is a certificate authority is a top-notch security-based company. And one of the things that really distinguishes them are their key ceremonies. This is what a key ceremony may look like. It's a bunch of people sitting in the room. There's technicians, there's people from all over the company. There's probably also some randomly selected people from, let's say, they picked up at the coffee shop or at the streets. And as soon as they need to change their private keys, because it's a good security practice to rotate them every now and then, they start this ceremony. There's a big book that describes how the ceremony should go. It's 10 to 16 pages probably, and it describes in very much detail every step that needs to be taken, from getting the current key materials from the safe, generating the new key materials, to putting them back into the safe. And the attendees, you can see them, they are sitting there with their notebooks and they're checking the box if everything happens according to the plan. Depending on the size of the company and the importance of the key material, there will be a number of cameras in the room. This is actual footage from such a ceremony, and they will record every little detail that happens in the room. The ceremony in itself can easily take 8 to 16 hours. That's quite a long day, isn't it? And everyone will dutifully note down if everything goes to plan and if there's any divergence, if that divergence is allowed. So, well, at least we can be sure that the companies that our digital infrastructure relies upon have their procedures in order, right? Looking at the time, I think I can do a little fairy tale here. This is the beautiful city of Beverwijk, which is a little town in the Netherlands, a little north of Amsterdam. It looks peacefully, doesn't it? There's some companies, there's some buildings, people live here, people work here. All was fine and good until one day something bad happened. Because one of the companies that was located in this city of Beverwijk was DigiNota. DigiNota has started out as a notary, a formal person, sworn in by the king, all fine, but they thought, hey, this digital certificate business, that's golden. I want to make some money there. So he started issuing digital certificates. And on one day, their systems came under attack. Some attacker found that their public website that was running on .NET Nuke software had a file upload vulnerability. And this vulnerability was exploited by the attacker to obtain access to one of the public website systems. Now, Windows password security being what it was back in the days, not so secure, he was able to find the domain administrator password. And the domain administrator password is actually very useful because you can more or less browse, traverse through the network infrastructure. Not having a really proper network segmentation policy or something like that, the attacker was able to find a machine that hosted the private key materials of DigiNota. Now, let me leave you a few seconds to think what this means. If we would have been in person together, I would just ask you, hey, what do you think this means? What this essentially means is that the attacker is able to generate any certificate to any subject and that the whole world would think that the certificate was trustworthy. So basically the attacker could impersonate as every website in the world, and probably did that, by the way. What happened in the days thereafter? Well, Google updated Chromium and blacklisted 247 certificates they found to be issued by DigiNota. Microsoft removed the DigiNota root certificate from all Windows versions that they supported back then. Mozilla did the same thing for their browsers, and Apple issued a security update, 2011-005. But wait, there's a little asterisk down there. This Microsoft update, there was something special with this Microsoft update. It wasn't rolled out to the Netherlands, at least not immediately. Why not? Well, DigiNota had one important customer, the state of the Netherlands. And all internal systems in the Dutch government were running and were secured by certificates issued by DigiNota. And the government was actually afraid that their clerks would be sitting, not being able to use the computer systems. So they kindly asked Microsoft to withhold the update for a little while until they would be able to update to replace their certificates. It's a bit as if I come home to find somebody has broken into my house using the key that's under the doormat. And they didn't take that much, so I'm happy with that. But they'll probably come back because now they know how to get into my house. But on the other hand, tomorrow is the day that the cleaner comes and cleans my house. And I don't want the cleaner to be locked outside when I'm at work. So I decide to leave the key there under the doormat, risking that the burglars will get back to my house and just basically take everything they find. Because, yeah, the house needs to be cleaned tomorrow, right? It's not really the right kind of priorities, I would say. And to make things even worse, and trust me, I'm not proud to be Dutch when I say this, so some government officials appeared on national television and they said, oh, people, you don't need to worry. Yeah, there's kind of a security issue, but it's really nothing to be concerned of. You just double check that there's a lock icon in your address bar when you navigate to any of our government websites. Well, that's especially the last thing that you need to do, because the whole thing is that this is not trustworthy anymore. anyone could have issued a certificate for whatever government website at that point. The eventual resolution was, of course, to update the certificate revocation list. These lists are maintained by the certificate authorities and are a long listing of all certificates that they once issued but should no longer be trusted. So there's time for a little quick demo. Just one more. And that is to show you the things that, well, the imperfections that we still face. What I did here, and you may have seen it, is that I went to Google with freeos.nl. And look at this, the check bar, there's still a lock icon over there. So my browser thinks the connection is secure. And I am actually having a secure connection to Google, but the connection is not trustworthy. The connection wasn't to Google, but the connection is to my own machine. Certificates can tell us whether the connection is secure, but they cannot tell us whether we connect to the entity that we expect to connect to. If we make a typo, transport layer security will not be of help. So I promised that it would be a practical session that we could use in our daily jobs. So the last few minutes, I want to share some basic tools, tips and tricks that you can help to troubleshoot whenever something goes wrong. First of all, very simple tool, CURL. It's just an HTTP client that supports transport layer security. We can give it an address to connect to. We can supply the verbose switch that will do a lot of debugging output. And if we supply -K as well, then it will skip certificate checks. So we can inspect what kind of certificates are sent over the wire. If we want to dive a little deeper, the OpenSSL binary has an sclient command which does the same, but in greater detail. Many issues arise from servers supporting different ciphers, different protocols, etc. And the Nmap tool comes with a built-in script called SSL enum ciphers that lists the ciphers that some server that we try to connect to is willing to support. And finally, we have SSL dump, which allows us to dump traffic on a certain network card and a certain port and a certain host address to the packet level. And if we supply it the private key, imagine that we have it, we can even decrypt the traffic on the fly. Now, if we move to the Java virtual machine, there's a bunch of important settings to know of. It's JavaX Net SSL Trust Store and Trust Store password. The Trust Store can point to a file that contains all the certificates our JVM, our running JVM, is willing to trust. The password of the default Trust Store that ships with any Java runtime environment is change it. But you can and maybe you should change it. But even better would be to supply your own Trust Store that contains only the certificates that you are explicitly willing to trust, for instance, because you checked the fingerprints. If your client needs a private key to connect to some service, then you can supply the key store parameter and the key store password. They follow the same file format, which is JKS for older Java versions or PKCH 12 for newer JVMs. And this format can contain both the certificates and the key material. You can put them in the same file, but you don't have to. Now, if you want to debug why your JVM does not behave in the way you expect it, when it comes to transport layer security, you can supply JavaX Net debug is SSL, optionally followed by a flag to select what kind of information you want to be visible in the debug log. And finally, there's a nice tool called Porteclay, which is a graphical skin around the key tool that ships with Java. The key tool is a command line tool. It's not very user friendly, but Porteclay is a very nice graphical user interface that lets you view your key store or your trust store, generate keys, import keys, etc., etc. So it's time for the takeaways, and those are public key takeaways, so you can take them with you in your day-to-day job. First of all, if anyone says to use SSL, don't do that. Use transport layer security, preferably at least version 1.2 or 1.3, as those are by far the most recent. Second, be careful with whom you trust. Look at your trust store, verify that the certificates that are in there are indeed the certificates that you are willing to trust and not some kind of a big company that may have issued a certificate. In the most cases, you don't need that, especially when it comes to system communication. And finally, when you are in doubt, when you want to investigate, open your toolbox to find the tools that you can use. OpenSSL, CURL, Nmap, SSL dump, Porticlay, that can be very useful to make your life easier, your work easier. So with that, there's room for questions. I want to thank you for attending, first of all. What kind of questions do we have?
We have one question from Andreas. And the second question. So the first question is why are still often talking about SSL and TLS if the one which is secure? And the second question is what is the difference between key store and trust store?
All right. So the first question is, why do we still talk about SSL if it is not secure anymore? And that's basically for historical reasons. It has been named SSL for quite some years, as we saw in the historical overview. People got used to the name SSL and then, yeah, didn't really change their jargon, their way of saying things. I often find people saying SSL, well, they mean transport layer security, but it's always interesting to double check if that's actually what they mean, because sometimes people say SSL and also mean SSL, so the very old and broken protocols. And as I said in the takeaways, please don't ever use them anymore. The good things to use are the most recent version of TLS. So there is kind of a naming confusion there, to be honest, and it's mainly for historical reasons. And the second question was about the difference between trust stores and keys stores. From a technical perspective, there is no difference. They are the same file format, they share the same semantics, and actually a trust store can be a key store as well. If I put my private key in the same file as I do put my trusted certificates in, then, well, they're one file, and I can just say to the Java virtual machine, here's my trust store, this is the password, here's the key store, it's the same file, it's the same password. The thing is, in many environments, especially the larger enterprises, a trust store can be maintained by a development team, which is allowed to change the certificates that the system trusts. Whereas the private keys, well, they are issued by some kind of security department, and they don't want anybody to see those private keys. So they just give a development team a JKS file or a PKCS12 file and tell them to load that file, and then they say, and when the application starts, we will put the password to that file in place, so that the application development team doesn't ever see the key materials. That's a very rigid approach, and it comes with a lot of challenges, but that's why you can specify different files for that. But in reality, you often see that teams just have one file that contains both of them.
Okay, and two more questions.
Sure.
How long it took for the government to replace their certificate? And obviously, how much did it cost them? On a lighter note, did the burglars came the next day in your store?
Oh, yeah. Well, the burglar was just an example. I am very lucky to have never found burglars in my house. So thanks for worrying. But that was just an example of how stupid I think what the reaction was to not roll out this update. It's, well, that's luckily it's just an example. So how long did it take for the government? I actually don't know exactly. I think it took them quite some weeks, given the speed that our government has when it comes to IT projects. And how much it costs, well, I really dare not to say. There's probably some kind of report that would tell me, but I don't know from heart. I do know that it was quite a big deal in the security industry in the Netherlands. Like, hey, how can you be so stupid to leave the door basically open by not revoking those certificates immediately? You could have given your employees in the government different instructions, like every time you access the system, look at the certificate and verify that it has this fingerprint, for instance. It's a very simple thing. Okay, it's more work, but still those people would be able to do their work. But right now, if the attacker would have come and would have issued any certificate to a government system, then there would be no way to distinguish that from the legitimate certificate. And that would mean that the attacker would basically be able to intercept traffic and read along. It is known that the attacker did issue some certificates for Gmail and other Google sites, or it's pretty surely known, not 100% maybe. As far as we know, there haven't been examples of certificates for the Dutch government systems to be issued, but you never know.
Okay, two more questions and we finish.
All right.
You said that TLS 1.3 is secure for replay attacks. Can you address the concerns of zero round trip potential replay attack, vulnerability mimicking real clients?
I'm not sure I understand that question correctly. Could you please repeat that?
Can you address the concerns of zero round trip potential replay attack, vulnerability by me? I'm not sure if
yeah, I'm a bit in doubt. I don't exactly understand the question, which makes it hard to find an answer to that question.
So I think the question is about a round trip potential
Yes.
replay attack. And if mimicking real client can help you address this concern.
Yeah, I don't have an answer on that one right now. If the question is written somewhere, I would be really willing to take a look at it and see what I can understand from it. But
yeah, in the toolbar in the Zoom you have Q&A.
There's a Q&A. Let me see if that. It doesn't come up, the Q&A. Maybe it's because I'm in full screen. Who knows? Ah, there it is. The TLS 1.3 is secure from replay attacks. Can address concerns of zero round trip potential replay. No, I did not precisely say TLS is secure from replay attacks. What I said is there is no published attack on TLS 1.3, but the whole problem with security, of course, is that if someone finds an attack and doesn't publish it, we are all under the assumption that we are using something secure, while it is not secure. Now, the concerns of a zero round trip potential replay attack mimicking real clients. I would need to dive into that. Even when I read it, I can't understand the question. So that's a bit hard to answer.
Yeah, and the last one.
I'm sorry for that, Ivan. Your question is just too hard for me.
The last one. When working with certificate internally or facing customer, it is very tempting to use self-signed certificate and distribute the public key. Would you compromise security with this?
Well, that question I do understand, so that's a good part. It is very tempting to use a self-signed certificate. I would say for internal systems, it can even be enough. It really depends on your requirements, of course, but it can be enough, especially if, for instance, I make those certificates and somebody else needs to check their connection with me, then I could print out the fingerprint, give it to them and say, well, please verify if this is what you see as well. We're good to go. Huh? If their key store contains only if their trust store contains only my self-signed certificate, for internal purposes, it might be good. For public facing systems, I'm a bit hesitant, especially since the last years we've seen the growing popularity of Let's Encrypt, which makes it essentially free and fully automatable to obtain a certificate that is trusted by every browser. So what keeps you from doing that and making it more secure than having this self-signed certificate?